All right, so we have one last example to talk about for optimization. And this is the one that's going to require the most work. It's not terrible, but we're just kind of building up in difficulty with each one of these. So in this one, we're looking at a rectangular box with a square bottom and a closed top, and it's to be made from two materials. The material for the sides costs $1.50 per square foot, and the material for the top and bottom costs $3 per square foot. It says if you're willing to spend $15 on the box, what is the largest volume it can contain? And then it says to round your answer to 3 decimal places if necessary. Okay, so once again, this is another example where it lends itself to a picture. You're going to want to start by drawing a little picture of this box that we're working with. And try to pay attention to the details that are given to you in the problem regarding this box. There's a couple of things that are important. One is that it has a square bottom, okay? So at the bottom, I have a couple of edges, and you're gonna wanna label the dimensions of this box, length, width, and height. But the fact that it's square on the bottom means that if I call that edge X, then this is also X. In a more general case, I would probably call this X and that Y, because I don't necessarily want to just imply that they're equal, but we know that they are because we're told that the base is square. The height is not related to the length or the width of the base at all, so I'm going to give that a different name. Let's call it Y. And then the other thing that's mentioned in the first sentence is that it has a closed top. You'll see these types of box problems in a couple of varieties. Some where the top is closed, others where the top is open. And the reason that matters is because we have to account for the material that it takes to make the top of this box in this problem. In a different problem, if it says that it's an open top box, then you consider there to be no material on top, and that will change your objective function. So let's first look at what our objective function should be. It says if you're willing to spend $15 on the box, what is the largest volume it can contain? So I'm trying to maximize volume. Maximize because it says largest. How do you find the volume of a rectangular box? Well, volume is equal to length times width times height. So x times y, or x squared times y. Now, just like our last problem, I have an objective function, but it has too many variables in it. So once again, we want to come up with a constraint that we can use to make a substitution somewhere, which will reduce this down to a function of only one variable. And that's kind of the same thing you're going to see over and over again in these optimization problems. Where will that constraint come from? Well, notice here it says, if you're willing to spend $15 on the box. So I have a fixed amount of money I'm allowed to spend to build this box, and then I'm told how much it costs to build different parts of the box. So it says the material for the sides costs $1.50 per square foot. Let's deal with the sides first. Okay. First of all, when we're talking about building the material, notice it's using square feet. That's a measure of area. So we're paying for this thing according to the area that each face of this box occupies. So if I wanted to find the area of all 4 sides, because there are 4 sides to this, sometimes we'll draw these little dashed lines to show like the back of the box. There's 4 faces, and each face has a base of x and a height of y. So each face is a rectangle whose dimensions are x by y. The area of that is going to be x times y. And there's 4 of them, so I have 4 x, y. Now what that accounts for is the area of all 4 faces along the sides of this rectangular box, but it does not account for the cost. So what this would give me is the number of square feet that those sides occupy. But then I have to multiply that by 1.5, that's $1.50 per square foot, to account for how much they cost. So that can be simplified. 1.5 times 4, which would be 6xy. So this is going to give me the cost of building the sides. What about the top and bottom? Well, if I kind of mimic what I did there, I can see that it's going to cost $3 per square foot. So I know I'm going to be multiplying something by 3. And the thing in here should be the combined area of the top and the bottom face of this thing. Well, the area of the bottom is x times x, which is x squared. The top would have the same area, so 2x squared is the cost, or the area of the top and bottom combined. This multiplies out to 6x squared, which is the total cost. Okay, so if we let C represent the cost, in fact, let me back that up. We don't need to call it C. We know exactly what we're spending on the box. It's 15. So if I were to add these up to get the total cost, 6xy plus 6x squared, that's going to have to equal 15 because I'm assuming that I'm spending all of my money to build this box. I want to get the largest volume possible. It would not make sense to keep some of that money. This right here is my constraint. Because remember, this is not the thing I'm trying to optimize. This is the thing I'm trying to optimize. However, this imposes a relationship between x and y. So what I need to do is solve this for one of those variables. It'll be easiest to solve for y, then use that as a substitution up here. So to solve this for y, one thing I could do is divide everything by 6 to start. So I'm going to get xy plus x squared equals 15 divided by 6. 15 divided by 6 would be 2.5. Okay, then to solve for y, I would subtract the x squared from both sides, so I get xy equals 2.5 minus x squared. And then to solve for y, I would divide everything by x. So now I have 2.5 over x minus x. That's what y is equal to, and this is what I would use as a substitution for the y in my objective function. So now I can call my objective function v of x. It's volume, that's what the v stands for, but it's only going to depend on x because I can write it as x squared times this instead of y. 2.5 over x minus x. Okay, distribute that x squared in because it's going to cause some cancellation there. I'm going to get 2.5x minus x cubed. Okay, so now I have the function that I want to optimize. The next thing I would want to do is find the critical numbers. I don't know why I was blanking on that for a second. So once again, take its derivative, and the derivative here is going to look like 2.5 minus 3x squared. And we can either look for where this is not defined, which is nowhere, or we can set it equal to 0 and solve. Okay, now the solutions here, if I solve this for x, I'm going to skip the algebra because that's very straightforward, but what you're going to end up with is the square root of 5/6. Okay, now technically you would get two solutions out of this. You would get plus or minus the square root of 5/6 because, again, with the last step in the algebra here would be taking square roots of both sides of an equation, and you always get that plus or minus. I'm not writing plus or minus though, because in this problem, negative values of x would not make any sense. And this is what I had mentioned at the beginning of this section, where when you're looking at these functions, this is we have a cubic function here, but when we took a derivative, we found a quadratic function. These are defined for all real numbers, but if you think about what this represents, not all real numbers make sense as inputs. X represents the length of a box, or one of the dimensions of a box. It can only be a positive number. It wouldn't make sense in any other case. So square root of 5/6 is the only critical number that would matter for this problem. At this step, what I would like to do is start plugging in or start verifying whether this gives me a maximum or minimum value. Now, I've been using the second derivative test this whole time, And that would still be a really good test to use, but just for variety, I'm going to do the first derivative test. So for the first derivative test, remember, we're going to set up a number line. And remember, I'm putting 0 on there because this thing is not, our function is not going to make sense if x is negative or even 0. So this represents sort of a boundary to the left. Then I'm going to put here the square root of 5, 6. Okay, that's my critical number. What I would like to do is pick something to the left and to the right of that square root of 5, 6, plug it into my derivative and see if I get a change from increasing to decreasing, or vice versa, or neither. So we need to pick a test point over here. Now you can plug that into a calculator and get a decimal to see what I could compare my test points to, but 0.1 is smaller than this. So I'm going to plug 0.1 in. What is v prime of 0.1? Well, that would equal 2.5 minus 3 times 0.1 squared. Okay, 0.1 squared is equal to 0.01, so this is equal to 2.5 minus 0.03, right? Now, I could keep going with the arithmetic here, but notice 0.03 is most definitely smaller than 2.5, so when I subtract these, I know for sure that's going to come out positive. So over here, v prime is positive. Now pick something to the right. Let's say x equals 1. That's larger than this square root of 5, 6 here. If I try to find v prime of 1, that's 2.5 minus 3 times 1 squared, which is 2.5 minus 3, which is easy to do, but more importantly, 2.5 is smaller than 3, so this subtraction will give me a negative number. For sure it will. That gives me a negative. So that means my function is going from increasing over here to decreasing over here. That's a maximum value by the first derivative test, okay? So before I jump to an answer, let's look at the question and see what it is we're trying to find. What is the largest volume it can contain? Well, what I just found is an x value at which that maximum value will occur. But what I need to do is find what the actual volume is when I plug this in. So I'm going to find v of the square root of 5, 6, because now I've confirmed using my first derivative test that this will give me a maximum volume. V of x, remember, is this function right here. So that's equal to 2.5 times the square root of 5, 6 minus the square root of 5, 6 cubed. Use a calculator for that. This is going to come out to approximately 1.521. Okay, so now let's state our conclusion by the first derivative test. The maximum volume of the box is, I'm going to say approximately 1.521. Now think about units here. So coming back up here, material is the material for this box is measured in square feet, which means the linear units for the edges would just be feet, which means the units of volume would be cubic feet. So 1.521 feet cubed is the correct units to be using there. That's my conclusion. That's generally how you want to state your answers to these problems. Okay, so once again, that's only 3 examples. It's a fairly limited selection of problems that we do optimization on, but because again this class has such a narrow focus, these are the kinds of examples you're going to be seeing over and over again in the homework. There will be a little bit more variety in the homework, but I want you to think through how you might solve those based on what we did here. So that's where we're going to go ahead and end this section and chapter 3.